I'm honored to introduce you, Professor Ginny Sabin. And first, I'd like to express our sincere appreciation to Professor Sabin for agreeing to deliver this talk to our colleagues and students at PolyU. Professor Sabin is one of the most brilliant architects, designers, and artists I know at Cornell. This is true, okay. Professor Sabin is now the Arthur L. and Isabel B. Wiesenberger Professor of Architecture in the Department of Architecture of Cornell University. And she's also the founding chair of a new department called Department of Design Tech at Cornell. Sabin obtained 2 bachelor degrees, Bachelor of Fine Arts and Bachelor of Arts degree from University of Washington in 1998, and also a master's degree in architecture from University of Pennsylvania in 2005. Now, after practicing in her own studio and also lectured at the University of Pennsylvania for some years, Jenny joined Cornell University's Department of Architecture in 2011. It's about the time when I also joined Cornell. Sabin's work is highly cross-disciplinary, and she draws inspirations from biology and mathematics, and uses a wide range of materials, including ceramics, optics, organic materials, as well as textiles, and to create architecture installations with astonishing visual impact and function. I was really honored to have worked with Professor Sabin when I was a department chair of fiber science and apparel design, and Professor Sabin was one of our field members of fiber science and apparel design. And for her outstanding work, Professor Sabin has been honored with a number of prestigious awards, including the Field Fellowship in Arts for work in architecture and design, and United States Knight Fellowships for architecture and design, as well as the Architectural League Prize for Young Architects from the Architectural League of New York. No doubt to me, Professor Sabin is was a rising star and now is a highly accomplished architect and design with amazing achievement. And so without further ado, let's welcome Professor Sabin. Yeah, so thank you. You may not be able to hear the applause, but the stage is yours, Professor Sabin.
Wonderful. Thank you so much for the kind introduction, Jintu. It's really a sincere pleasure to be here. Thank you to Hong Kong Polytechnic University, and also to you, Jintu, for the invitation to join you today to talk a little bit about what I do. And you provided a really great overview, so thanks so much. Today in my talk, I will be presenting several research projects from my lab at Cornell University. And I will also be presenting several projects, built works, applied work that we have developed in my practice, Jenny Sabin Studio. So I'll go ahead and share my screen. more time. Great. Is that showing up okay on your end?
Yes.
Fantastic. So the title of my talk today is Biosynthetic Design Towards Adaptive Architecture. And in many ways, transdisciplinary design and technology have never been more important. We find ourselves recovering from the depths of a pandemic and an urgent climate emergency upon us that demand that design and technology come together to cultivate new collaborative models, importantly across disciplinary frameworks that are not about silos, but working collaboratively and laterally across disciplines. At the same time, 3D printing, advanced manufacturing, and robotics are transforming how we make, construct, and build across disciplines, engaging technology, industry, design, practice, and beyond. This also opens new possibilities for sustainable construction processes to reduce waste, save time and labor. And indeed, in many ways, our biggest asset is our creativity, our ability to work across disciplines, to come together and to collaborate. Recent advances in computation, visualization, material intelligence, and fabrication technologies have begun to alter fundamentally how we design, construct, and make from the nano to macro scales. For example, we ask, can buildings be made more responsive through the integration of artificial intelligence and big data? These new intersections between the biological, the digital, and the physical are radically altering the way that we work from the nano to macro scales. I believe in the not so distant future, materials will not just be elements and things and buildings, but they will generate immersive and adaptive regenerative structures. So like the cells in our very own bodies, sensors and living architectural materials will learn and adapt, making materials not only smart, but also importantly, cyclically engaged with local environments and resources through ecological feedback loops. We need to radically depart from traditional research models in architecture, science, and engineering with a move towards hybrid, transdisciplinary concepts and new models for collaboration. One approach that we developed as early as 2005 entails the hybridization of labs and studios to fuse innovations collaboratively across science and architecture, to fabricate next generation architectural materials and structures that are adaptive, sustainable, and resilient. And this is a photograph taken on the first day of a course that I co-taught with a longtime collaborator, the late Dr. Peter Lloyd-Jones, who was a cell and molecular biologist. And the title of the course was Nonlinear Systems Biology and Design. And this was also in the context of Lab Studio, which we were told at the time was the first example of a truly collaborative hybrid research and design space shared between architects and biologists. This mode of working has contributed to a body of fundamental research and applied projects that emphasize design research as a continuous and emergent process. At a time of sociopolitical and ecological catastrophe, grounded on our deeply entrenched misconceptions of human and cultural dominance over nature, biosynthetic architecture has the potential to open new models and approaches for how we teach, how we conduct research, and how we practice and engage with industry. My collaborative teaching, research, and practice focus on the contextual, material, and formal intersections between architecture, science, and emerging tech to innovate non-standard responsive building skins, biobricks, and tiles, and sentient spaces that are not only performative, but generate what author Jenny Odell calls, quote, attention-holding architecture, end quote. One of the fundamental questions that we pose in all of our work is how might buildings and their integrated material systems respond and adapt more like organisms do in their local contexts. We integrate the premise that nature is resilient, not efficient, into our thinking and methods. For example, human design systems frequently prioritize efficiency to maximize output through the minimal use of resources to increase productivity and performance. And in contrast, nature develops incremental redundancies and biodiversity to adapt to changing environmental conditions over longer timescales to ensure robustness and sustainability within a system. We think that's a pretty amazing and robust way of thinking in design. We embrace transdisciplinary design with a focus on problem and knowledge generation over immediate problem solving through collaborative design research models that transform and evolve over time. So we typically don't start off with a specific problem, but allow for those problems to emerge through a shared process. And then, of course, we solve those problems that emerge collaboratively. So with strong links to my lab at Cornell AAP, the driving mission behind my practice and research is to create resilient, science-driven, and transformative spaces with and for diverse communities. This interest importantly probes the productive tinkering and misuse, deliberate misuse of fabrication machines that are often found in alternate industries and disciplines, such as in the textile industry, in medicine, and beyond. And this is, of course, informed by issues of making and craft to produce analogically biosynthetic material systems and software tools that have the capacity to hopefully embed and facilitate expression within our built environment. So a seminal reference for this work is the extracellular matrix. This is a dynamic protein network that physically and chemically connects the exterior environment of cells with the interior and vice versa. Essentially, the big idea here is that half the secret of life resides outside of the cell. So you have DNA or code, but that DNA is acted upon by external environmental events. And so in working with Peter and his students, developing Lab Studio and doing deep, rigorous research into morphogenesis, surface design, and changing morphologies in various biological systems, this presented to me early on a series of very powerful ecological models to bring back into design. A notion of thinking dynamically about how environment affects the development of geometry, material, form, history, program, event, and beyond as a set of inextricably linked conditions and parameters. So an important takeaway is that we have never been interested in simply taking a biological data set or a biological form and scaling that up into architecture or applying it as a pattern, but to look at the processes and behaviors that are governing those emergent forms and morphological changes, which then move into a set of tools and analog applications. So we focus on process and behavior to bring that back into design as bioinspiration and at times biomimicry. So an early project, eSkin, which was a 4-year research project funded by the National Science Foundation. In this project, we emphasized heavily upon the study of natural and artificial ecology and design, especially in observing how cells interact with pre-designed geometric patterns and how these patterns are altered to generate new surface effects. And I won't talk about this in too much depth, but I just wanted to highlight one of the principal topics that we worked on in this project that continues in my core research and in my applied work, which is the topic of structural color. And structural color is not based on changes in pigment, but it has to do with how a particular wavelength of light is interacting with a nanoscale material, oftentimes found in nature, such as the wings of certain butterflies, the blue morpho butterfly, or certain seashells, such as the abalone seashell. And in turn, how those changes alter our perception of color change and dynamic switching from transparent to opaque and vice versa. So you see here on the right, our first full-scale prototype of the eSkin. This took us 2 years to develop at the lab bench side and in the studio to exhibit dynamic switching from opaque to transparent, and of course, a change in color. Running concurrently with the eSkin project, we were able to develop and apply the fundamental research concepts that were emanating collaboratively from the shared labs in this project. And this was a really important commission that came to me from the College of Human Ecology, where I met Jintu when he was the chair of fiber science and apparel design. And like many projects on university campuses, this took many years to develop, perhaps because it wasn't quite a building. It isn't a piece of sculpture. You can inhabit it, you can walk through it. So it took many years to surpass the hurdles that we had to in the context of a university campus. But that allowed us, importantly, to create some interesting threads between the core research, testing, fabrication tests, and eventually to apply these principles of responsive material structures in a built project on campus. The project importantly integrates community and environment to generate a responsive and ornamented architectural intervention that envelops and activates daily routines and exchanges between students, staff, and faculty. And I'm very happy to report that it is now a beloved project on the campus. And indeed, many people gather to see it changing on a daily and nightly basis. So in this case, structural color is achieved with a dichroic wavelength-dependent thin film that's laminated to tempered glass panels. And light reflecting from and refracted onto the film changes color and grows warmer or cooler, more opaque or transparent, and is not, as I just mentioned, based on pigment, but how the film selectively interacts through interference or reinforcement of certain wavelengths of light at the microscopic scale. A key component to this is how we perceive those subtle to dramatic changes of light and color within the material itself. And here are some views of it at dusk. There's an integrated lighting system on a sensor, so you can see how that changes from interacting with the sun throughout the day and then with the lighting system at night. So in discerning which effects and materials are actually scalable, we typically work across 3 phases. We start with the development of tools, scripts, algorithms, simulations to model behavior. Remember, I just said that we focus on processes that emanate from primarily biology, but sometimes we might start with a specific mathematical concept or a geometric concept based on, for example, kirigami, which is like origami, but with the addition of cuts and holes. And then those tools are brought into prototyping. And this is where we start to really grapple with scale. So with the eSkin project, the first experiments with an organic polymer, which was our starting point for exploring structural color and plating live human smooth muscle cells on those organic polymer substrates to see how they would alter patterns and geometry as a beginning point to capture those behaviors and then translate that into a series of responsive sensors and imagers. We found that actually scaling that was going to be extremely difficult. One, because of labor and time and just cost. And so we found an alternate material for that prototype that we just saw, that exhibited the same characteristics of the PDMS organic polymer substrate in terms of structural color, but that which could be scalable. And specifically, we worked with nano colloidal particles as a solution sandwiched between two pieces of conductive glass, ITO glass. So that's just one example of how we start to think about scalability and sustainability, and also at the same time integrate novel digital and robotic fabrication strategies. And then finally, some of those successful prototypes are brought into the realm of building and issues of the built environment. So it's a purposefully slow process to work in a rigorous fashion, to collaborate, importantly, across disciplines, and that takes time to do it well and to do it in a meaningful way. And also, again, to manage how we negotiate scalability. So in addition to designing at the architectural scale through projects and experimental prototypes with responsive materials that engage structural color and wavelength-dependent properties, we frequently design and fabricate environments that change and respond to live dynamic data sets, such as this project that we recently finished. It's a permanent project sited in the new Google Bayview campus, designed by Bjorka Ingels Group, BIG, and the Heatherwick Studio in Mountain View, California. And so we were commissioned for this important project. There are two projects, a tall tower and also a double membrane structure that envelops a stair. So in this project, affectionately called Eddy, which is the tower, and Shroud, which is the membrane structure, they engage the sort of undulating and multi-tiered canopy structure, which you can see here in that image on the right, and are also punctuated in this case with the tower by a supporting column, a staircase, and enclosed volumes. And these are some line drawings to highlight how the two come together. To generate the form for the tower, thousands of reclaimed yarn spools are held in continuous tension with a soft web of elastic fabric components, and the 42-foot tall stainless steel diagrid structure, which forms the primary structure of the tower, wraps and integrates with one of the columns that supports the canopy system above. This also engages a set of spatial relationships in terms of view and one's sort of association with it as a wayfinding device across this large campus. So you can see here how the cones, which were repurposed, become voids in the material system to allow for light to penetrate and emanate throughout. Now, the other project, Shroud, operates as a functional threshold to courtyard number 10, and also shares material and formal strategies with the tower structure. So the design process for both of the projects began with a comprehensive site analysis of our selected courtyard, including structural analysis of the column and stair. And to engage the building fully, I was really interested in how we might integrate with existing architectural elements, and that being the column and the stair in this case. And probably the most interesting takeaway from this project in terms of our data-driven, responsive architectural applications is the lighting system and how that interacts in real time with a live data set. So the proposed lighting system is driven by the flutter of live wind data, which is captured and integrated into a custom design software and hardware pipeline, which allows for a subtle changing spectacle of light, color, reflection, and shadow. So named after the physical phenomena of waves undulating across the grasslands, the tower Eddy features a data-driven lighting system that's steered in real time by wind data gathered from the local environment. And the new Bayview campus complex is sited in a really beautiful biome, which we did quite a bit of research on, and took the sort of point of departure of integrating it in some way through the data sets within the project itself. So here are just some details. You can imagine how much work went into these custom designed and fabricated components, including testing and 3D printing the inserts to delicately hold the cones on either side, and then also tension the double membrane component elements. And some additional views looking up. So this was just finished this past year. So in addition to innovating adaptive and responsive materials, we also work with non-standard components and specifically working with rapid manufacturing and 3D printing. And we do a lot with clay material. Jintu mentioned that I have a background in the fine arts. I have a BFA in ceramics and was a practicing artist before I ventured to graduate school to do my professional degree in architecture. And while I thought I left that life far behind, I realized that I literally had a body of material knowledge that I could bring to a different context. And so in 2009, we purchased our first powder-based printer, and I started to tinker with the material recipes. I took out the proprietary media, and this is 2009. There was not a whole lot happening in 3D printing yet. And we successfully printed our first clay non-standard components, which absolutely blew me away. And so this, over the years, the last decade, has led to a series of seminars and option studios on the topic of digital ceramics, representing over a decade of research, innovation, and teaching. And in my lab, we have focused on bricks. I thought bricks were an interesting point of departure. One, they're accessible. Everybody knows what a brick is. And two, they haven't changed a whole lot in terms of how they're made and produced because of the process. But with the advent of 3D printing, every single brick can be different. You can have porous bricks. You can begin to look at different strategies for how they connect without mortar, vary the geometric approach, and so on. And so this is Polybrick 1.0. This is now part of the permanent collection at the Pompidou in Paris, which I'm proud to report. And Polybrick 2.0 turns to nature. So once we resolve some of the technical and material hurdles with the first version, we turn to nature for a set of design drivers. And specifically, I was interested in looking at human bone. One, to optimize for how load paths travel through a brick. For example, if we were to look at the CT scan of a runner versus a bicyclist versus a swimmer, the density of that bone would look different based on those repeated load events. We think that's a pretty awesome way of thinking about how we optimize for load paths within a brick. And that also opens up possibilities for bricks being highly porous, extremely lightweight, but very robust. Designing with the paradox of building with holes, which we see everywhere in nature. And so that's been in collaboration with Dr. Hernandez, who's a mechanical engineer at Cornell, whose expertise is in the mechanics of bone. The project that I'm going to focus on a bit more this morning and afternoon is focused on the question, how might we rethink building materials through 3D printing and biologically informed design? And this is Polybrick 3.0. This has been a multi-year collaborative project with, again, a longtime collaborator, Dr. Dan Lau, who is in biological and environmental engineering at Cornell. And in recent experiments in my lab, this mode of bioinformed thinking that I've been describing has now expanded to directly designing with life. And this has been achieved in collaboration with Dan and his group through DNA-steered ceramic materials and living glazes that exhibit dynamic feedback mechanisms. So we're reflecting upon new questions of adaptive and responsive materials through the integration of advanced processes in both 3D printing, but also in the engineering of DNA that is integrated with hydrogels. And this is in the context of Dan's group and his expertise. So we're exploring programmable biofunctionalities and developing these living glazes for biotiles. And the exciting thing is that we're actually working at scale. In the first phase, we went downscale to test and tinker and develop a set of strategies that we could then bring to an actual tile geometry. So here are some images from that first phase where we're testing fluorescence. So we were specifically working with a DNA sequence that allows for the emission of light or fluorescence, and I'll come back to that in just a moment. So DNA is known as the information storage molecule for biological systems. It's also a known material in engineering. And so the first phase of our work has focused on using DNA to design with light, where unique signatures, which you can see in these first iterations, fluoresce within the polybrick clay body. So what are we specifically doing here? We're working with a DNA sequence based on what's called the luciferase, or what is known as the magical firefly. Everybody knows what a firefly is, but you may have not seen one in real life. They are indeed magical. So the input energy in this particular sequence is ATP, and the output energy is light. And so what this enables is cell-free production of light on ceramic tiles. So in Polytile 2.0, which builds upon this, we're taking this to the next level in terms of scalability, right? So we're coming back to this question of scale. What is possible at the architectural building scale? So these tiles utilize 3D printed patterning techniques that are then plated with the DNA hydrogels as a substance that is steered and engineered with sequences. And then we tune these surface effects both within the pattern of the printed tile, but also within the DNA sequence to program the material to achieve certain effects at the micro and macro scales. So imagine a wall that not only alerts you to local contaminants or particulate matter in your local environment, a living wall, through the emission of light, but then cleans the local environment through chemical and also biological interactions. So in many ways, DNA nanotechnology will open up new possibilities for creating nano to macro scale materials and architectural elements that can dynamically react to environmental cues and interact with biochemical and even human reactions. So our first phase has been focusing on interacting directly with the environment, and this is ongoing work in my lab. And if you're interested in taking a deeper dive into any of these projects, all of our published papers are downloadable on our lab website, sabinlab.com, on the polybrick work, and also our recent work with Dan and his group on polytile. So this last applied project that I'm going to spend some time talking about builds upon over a decade of work testing how these biologically informed concepts and adaptive materials can be applied experimentally in architecture to engage with diverse communities. And specifically, our work in artificial intelligence has focused on the following two questions that you can see here on my screen. So since 2012, we have been able to deepen and apply our ongoing research on responsive materials that engage the dynamic conditions of light and energy, such as structural color that I talked about earlier in my presentation, through the transfer of those concepts to high-tech, responsive, solar active and photoluminescent fibers. And this commenced with a commission that came to me from Nike in 2012, where we developed a pavilion called the MyThread Pavilion. And this was for the Nike Flynet collective. Following several new projects, including Polythread for the Cooper Hewitt Design Museum as part of their design triennial, we were able to take this work to an entirely different scale, at an urban scale, with our winning entry Lumen for the MoMA and MoMA PS1 Young Architects program, which we were fortunate to win in 2017. And this is a top a view looking from above down into the large canopy structure at MoMA PS1, which is in Long Island City in New York. The YAP program ran for 20 years and concluded in 2019. And the projects essentially become a backdrop for a series of events during the summer, during the very hot summer months. And I was very excited to take what we had been testing at the time for multiple years to actually work with existing environmental conditions and the path of the sun. So the project itself features over 18,000 square feet of digitally knit porous canopy structures. There are 3 42-foot tall tensegrity towers. You can see 2 of them in this photograph. There's also an interactive misting system that actually functioned quite well to reduce the just high temperatures, especially during the summer, beneath the canopy. So as visitors moved and interacted together underneath the canopy through a network of IR sensors, which would then flip solenoid valves, the whole misting system had this kind of immersive experience of breathing and sort of hissing and gently misting participants to cool the local environment. These are some drawings to give you a sense of the site. The site is given. These are the 2 courtyards that are a part of MoMA PS1 in Long Island City. And I was very interested, as in all of my projects, in working with the local site constraints. So the canopy structures literally stitch into the pore holes of the concrete walls where they are then tensioned. And then the towers, the tensegrity towers, lift the canopy structures strategically at certain moments. And some additional details of the tower. So the whole project was designed to be dynamic, to be changing, to be transformative, both in the structure. So the tensegrity towers added a sort of third envelope of equilibrium to the project. Down to the materials and how they responded and absorbed UV energy to change color and to emit light through the photoluminescent fiber materials that were digitally knit. I should mention the MyThread Pavilion that I very briefly mentioned was our first project to integrate whole garment CNC knitting. I've been collaborating with Shima Siki for well over a decade now, innovating and pushing each other. They, at the time in 2012, were primarily working at the scale of the body, the human body, through collaborations in fashion, such as Issey Miyake and others. And they had never done anything at this scale before. So we did a lot of R&D starting in 2012 and through the course of this several projects that I mentioned. And this was indeed our largest project to date. And people absolutely fell in love with it. And they also fell in love with inhabiting the cones, which are the longer sort of stalactite elements digitally knit that held the misting system. So they were also misting and spraying people with water. And here are some photos taken on warm up, which happened every Saturday, where DJs and artists would come to perform. And so for me, the success of this project was seeing how people took ownership of it, seeing how it was being used as a new type of urban architectural space. And so I think, well, I not only think, I believe that there is something within our biosynthetic design process that comes from biology, not as a direct translation, but as a way of thinking and a way of designing that embeds these non-standard behaviors and processes as a way of making, as a way of thinking about responsivity and adaptation, that can be truly transformative for people. And I had people come up to me and say, I come here every week to take my lunch because it makes me feel calm. Or I wish this was in my child's playground, or I wish this was in my local hospital because it would help people. And so those qualities and those conditions are really important in the built work and my practice work that emanate from the fundamental research and eventually get applied. So these are important factors that continue to not only inspire, but also inform how we approach projects and engage with clients. And then just very briefly, in one recent project for a really innovative developer in Abu Dhabi, Imcan, we designed and produced a permanent public beach activation project, and this time collaborated with Gore, who has innovated Gore-Tex. You're probably all familiar with Gore-Tex, to develop an entirely new photoluminescent ePTFE material that importantly could withstand the extreme conditions of the desert climate in Abu Dhabi, including sand and windstorms. So this was a really exciting moment in terms of our R&D within the studio. And here, yet again, another photograph taken on one of the warm-up days. Between 5,000 and 7,000 people would come to frequent Lumen and engage in the warm-up activities. So I'll use this image as a backdrop to state that our collaborative work importantly also includes a significant human component, both in how it's made through a hybrid approach of analog and digital design processes, but also through the active engagement with diverse communities in architectural and urban contexts. So we also oftentimes start our applied projects with a series of workshops, working with community participants, engaging in collaboration that eventually informs a set of participatory design drivers. So the last project that I'm going to talk about, and then I'll conclude so we have some time for a Q&A, is ADA. And this project by Jenny Sabin Studio was in collaboration with Microsoft Research. And this also co-evolved in a transdisciplinary context. I was fortunate to be invited in 2018 to be a designer in residence as part of their Artist and Designer in Residence program, AIR, that Asta Roseway founded within their Redmond campus in Washington State. And so in conjunction with this work, we have been exploring how artificial intelligence can personalize rooms and buildings. We started this project with our colleagues at Microsoft Research with a joint mission and aim to develop a project that would open up AI in terms of looking at issues of privacy and bias within the algorithms and the data sets being used to make that more transparent, and ultimately to create a project that would position humans as agents of change within this technological paradigm. So I'm going to play this in the background. Let me just make sure the sound is Turn off. Here we go. So in many ways, the spaces and environments that we inhabit influence how we feel and also how we act. And so working together with my colleagues at MSR, Microsoft Research, ADA is driven by individual and collective sentiment data. It's housed within Microsoft Building 99, which is where Microsoft Research is. And so through the integration of course, responsive materials that are digitally knit and emerging tech, a primary aim of the project was to promote and increase well-being through people's direct engagement with the project. So in terms of the components, the lightweight pavilion is composed of both data-driven, tubular and cellular digitally knit components that are held in continuous tension within a semi-rigid exoskeleton. You can see here in this view. The exoskeleton is composed of close to 1,000 3D printed nylon parts. The lighting system and materials of the cyber-physical architecture respond to human participation, as I mentioned, as both individual and collective sentiment, and I'll talk a little bit about that in more detail in a moment. And those live data feeds are then brought into a software pipeline, which includes a program running in 2 sites, one on an on-site PC and a program running on each of the Raspberry Pis within the brain ring, which you just saw being installed. And the PC software, importantly, continually queries data from a network of cameras where data is being collected in an anonymous way. You can completely opt out. The data is not linked to specific people. And these expressions are classified using Microsoft researcher Daniel McDuff's platform, which drives ADA. And here's just some views of the final installation. There we go. So an important aim of the project is, as I mentioned, to expand and inspire architectural engagement with humans. And these are a couple of drawings highlighting some of the details. On the right, you can see how the double surface is composed. So the entire surface is composed of whole garment digitally knit cones and cells, which clip into, on the exterior, the semi-rigid exoskeleton, and then form a soft surface on the interior. And so structurally, the cones actually behave like springs, right? So there's a great deal of equal and opposite forces running through the entire system. And then the network of LEDs run within the webbing detail on the interior skin here. So all you see, if you're sort of engaged and inhabiting the project, are changing conditions of light and color. And there are 3 tiers of lighting. There are external PAR lights, the integrated LED system, and then within the center of the project, there's a tensegrity cone that features a custom designed fiber optic sheath. This was the first time that we worked with fiber optics, which was really exciting because it allowed us to begin to program each one of those fibers in a unique way. So literally each fiber has an LED that's passing light through it to create this sort of subtle changing gradient of light and color. So more specifically, the sentiment data, so the cameras that are tracking changes in facial expression, is collected, sent up to the cloud. It's then crunched on by AI algorithms to statistically determine the probability of certain expressions. That then is translated to light and color within the project. So literally, one can change and drive the materiality of the project in real time. So in this way, the architecture of ADA augments emotion through aesthetic experience, thereby opening the range of sort of possible human emotional engagement with the project. Another important part of this project is that it's being used for active research. So the software pipeline was designed to be purposefully open in terms of its architecture. So any researcher at MSR can run their data through this pipeline, which allows them to look at the hidden structures of data in a spatial way, in a material way. And I think we're seeing across all disciplines, in the context of our ability to now generate abundant data, but our ability to make sense of that data hasn't caught up by any means, and certainly AI helps. But by being able to spatialize and materialize data through design and through the intersections of technology, design, science, and engineering, we're able to facilitate new ways of projecting and looking at those data. So that's an aspect of this project that I'm really proud of as a demonstrator project. So in many ways, personalized architecture in the context of Ada may sense subtle changes in human emotion through sensors and interfaces that detect changes in facial patterns and voice tones. And in the context of Daniel's work, who was my primary collaborator on this, he's developing tools that are being placed in environments for the elderly. So for example, one may not entirely know how their environment is impacting them from a health perspective. And so these very sensitive AI-driven tools can detect those changes and then therefore alert us to certain conditions that we may not even be aware of. And from an architectural perspective, I'm not only interested in how we embed aspects of health and wellness in our spaces and our materials, but these tools, for the first time, will allow us to design with phenomena, changing environmental phenomena, whether it's data emanating from our own bodies as biodata or data emanating from our environments, that we can now integrate and harness and design with in ways that were never possible before the advent of these tools, which is extremely exciting. These are just some diagrams and images highlighting, again, the network of cameras, the software pipeline, and then again, how that translates into changing conditions within the materials. Here you can see some visitors on opening night on the right. This group had just discovered that if they all smiled really big, that there was a dramatic change in the responsivity of the materials and the emission of light. So that was pretty exciting to see how these discoveries were being made. And just some final images. Again, top view here, you can see the brain ring of Ada highlighted. So all of the Raspberry Pis and the hardware infrastructure is housed within that ring. And you can see all of the cabling bundled, which goes back to the on-site PC. So in many ways, Ada is a demonstrator project. It showcases the capacity and future of architecture to promote and increase well-being through the direct engagement with the spaces that we inhabit. And I believe that biosynthetic transdisciplinary design is about connections and synergies across science, technology, and architecture. And this is importantly steered by the systemic and relational conditions of life, in our case, from DNA to sentiment, as future adaptive and intelligent materials, and also importantly, the optimism of possibility. So we have been fortunate to receive support from a number of industry partners and federal granting agencies such as the National Science Foundation, Autodesk, and beyond. And if it was not clear, hopefully it was throughout my lecture, I operate with amazing teams, amazing collaborators, both within my lab and my practice. And I highlighted a few projects. You can find us at our websites here, as well as the published papers. And I invite you also to take a look at our brand new multi-college Department of Design Tech, which is in collaboration with the College of Human Ecology, Cornell Tech, Engineering, Computing and Information Science. And we are the administrating college, the College of Architecture, Art and Planning. And our first degree program, which is a Master of Science in Design Technology, kicks off this fall with our first cohort of students. And we plan to launch a new PhD program within the next couple of years. So stay tuned and do be in touch. And with that, I will conclude the formal part of my talk. And I thank you for your attention and for joining. And I look forward to your questions and engaging in the discussion.
Well, thank you, Ginny, for the most inspiring talk. Now, so it's a Q&A time. Any questions from the audience? Maybe let me start first, so that other colleagues get ready. To me, it's the most amazing. You know, you can integrate or you can bring together so many different disciplines together, right? From as far as from mathematics, biology, mechanics, robotics, artificial intelligence, and many different kind of materials bring together and to create something beautiful and very useful, and also consider the needs of interaction with the people using this facility, and also taking advantage of the environment, like lighting, temperature, and also collaborating with so many different kind of collaborators, which is not naturally, I guess, not your field, like Microsoft, Gore-Tex. You are architect. You know, how can that happen? You know, it's like multi-dimensional, but I lost the word. It's not just a one or two or even 10 dimensions. It's like hundreds of dimensions, right? You are bringing them together, creating something very unique, and you know, really eye-provoking, I would say. You know, it's refreshing, and yet it's also a very, very useful, functional thing. How can that happen? Is it just your kind of intuition? You're so talented, you're born to be like that, and you have a, you know, kind of free spirit to do that, or you have some kind of systematic approach? You know, so what is your thought process in all this, in doing this, and can somebody, you know, starting maybe a design career or even a technologist, you know, who wants to be creative, can they learn this kind of creative process?
Thank you for your excellent question, Jintu. I would say the first thing that I'll say is that the success of my work is fundamentally about relationships and people. And collaborative work cannot happen without care and time. And I think that's where perhaps a lot of people get it wrong. And I'll describe this with an actual sort of contextual story. When Peter and I met, he's the cell and molecular biologist that I started Lab Studio with when I taught at Penn for 6 years before accepting my position at Cornell in 2011. Before we actually launched Lab Studio, we knew that we wanted to do something together, but we spent a year sharing in each other's environment. So he would come to my studio reviews. I would attend his weekly lab meetings. He was completely freaked out by the culture of the critique in the context of architecture. He thought we were horrible to our students. And I had to let a lot of information sort of pass over me and remember my disciplinary core, my area of expertise. But it was throughout that year that we realized that while we shared many terms, we had very different definitions for those terms in the context of our disciplines. We developed trust. We figured out how to talk to each other, how to communicate effectively. And I think that investment of time was one of the most important early actions, that we took to be successful. So I think one element to success is taking the time necessary to cultivate trust within your collaborative relationships. Two, I've been at this now for close to 20 years, and which blows me away. It seems like yesterday was 2005. And I think I now have a honed intuition through experience of understanding who to look for, when we're launching a collaboration and maybe there's a missing component of expertise, or there's a particular, material system that we need guidance on. And also whether or not a collaboration is going to go anywhere. So part of that is just experience and now having a honed intuition on how to navigate these spaces. And then maybe the third thing, which is very important, and I mentioned this at the start of my talk, I'm trained as an architect, and the methodology that I was taught and now what I teach and what I practice is, I think, increasingly relevant, right? Design and the methodologies that emanate from design, the design arts, whether it's architecture or product design, engineering design, etc., presents a way of navigating a set of complex relationships, formulating a plan, and moving forward, and iterating and launching a process. That way of thinking, the rigor that exists within that synthetic process, I see becoming increasingly more important. And it's not bound, for example, to architecture alone or product design alone or other design arts. And I think we're seeing the blurring of our disciplines because it's a necessity. The problems that we face are too big, and designers and architects need to position themselves at these collaborative tables, and to bring our disciplinary expertise to that. And so I think that's been a huge part of my expertise. A huge part of my success is realizing that my expertise has relevance in science, right? It's never been about, me coming in and doing pseudoscience or trying to become a scientist, but collaborating with scientists as an architect, as a designer, and bringing that expertise to their science and how they do science, and vice versa, bringing the relevance of the scientific process into what we do. And the launch of the new department, together with my dean, Dean Min-Jin Yoon, and the participating deans and the inaugural faculty, honestly, for me personally, is such a milestone. And these things are hard to do. It's often been a long and lonely path, but I'm super encouraged and optimistic because we're seeing more models like this happening. So I hope I've answered your question, but I think that just in summary, the three components of my success are: one, taking care of relationships, taking the time to nurture them, to develop trust, to always cultivate respect, in the collaborative environments, and realizing that takes time. It can't happen overnight. It's not like you just go and knock on a biologist's door and say, let's do something. You know, it takes conversations and time. The second is experience, you know, and realizing that you have to put that time and effort in. And the third is the relevance of our expertise and how that can successfully bring about these types of collaborations, which otherwise may seem really daunting to bring together.
Yes, yes. So I feel that I think you must be very, very talented. You're a great observer in interacting with different kind of people in different environments. But I think my take-home message from your sharing is that be proactive to reach out to people with different expertise. But also importantly, when you're trying to reach out more people in more diverse different kind of fields, and then have more emphasis, you know, on what you can offer, what your expertise, you know, is. I think that is also very, very important, you know. Otherwise, you're losing yourself, you know, in this process. Yeah. So thank you. Yeah, yeah. I think I got your message. Yeah. And
Yeah,
yeah. Sorry. Yeah. Go.
I would maybe add one more thing, which is related to what you just summarized. Is that you absolutely need to push yourself into uncomfortable areas. You know, we get too comfortable in our silos, and you know, the people that we know, and to make these types of innovative cross and transdisciplinary collaborations work, you have to push yourself into areas that are unknown, and you know, to be brave and know that you have something relevant to offer.
Yeah, thanks. Yeah, I got another question. Because we are in fashion and textiles. I mean, you have created all these amazing architectural installations, which are mostly fixed, or would say relatively more rigid. But of course, the creation you made is much more flexible, much softer than many of the architectural installation. Installations. But our fashion and textile forms are even much softer, and it's moving, is constantly changing, and it has a much closer interaction with the body and also perception. And on top of that, we have to, or we want to sew the clothing into the washing machine to wash, and then take it out, and we expect looks the same. And also can be recycled, because we are, you know, consume much more clothing than what we really need. And this is really a big issue, environmental issue. So the whole, probably the fashion and textile, I would say not only the form of in terms of clothes, but also the whole industry maybe we need to be redesigned, to fulfill really the need of mankind in covering themselves or presenting themselves. Yeah, so any source, any advice to our field in fashion and textiles?
Yeah, I mean, as you know, I've been collaborating with experts in the fashion and textile industry for some time now. And we always, where we can, attempt to use, repurposed materials in innovative ways. So I think the work that's happening in research and also in industry that incorporates the reuse of textile materials as a circular fabrication process, I think is super exciting. Circularity in construction and architecture is finally starting to take off, at least at smaller scales. So those types of methods and ways of approaching sustainability holistically, I think are promising. But as you articulate, it's a massive problem. But I find the innovations in terms of how we approach sustainability, both in the textile industry, but also in architecture, that are not just about kind of metrics. So in architecture, we have metrics that, like LEED, which are important, right? Where you can check your newly built building against certain performance factors. But they're short-sighted because they don't look at the sort of history of the site. What happened at the site? Was there a previous building that was knocked down, right? There can be other factors in that story of a building's construction, its design, making, and construction that are not sustainable at all, right? Mm. So I think approaches that are much more holistic, that are not just looking at this generation, but multiple generations. There was a keynote talk by Dean Dory Tunstall, who is the first Black dean of a design school in North America. And she's very interested in approaching design from an indigenous perspective, right? So she poses the question, like, what would it mean to have an indigenous approach to how we design, where we're not just designing for this generation, but we're designing for 7 generations ahead, right? So I do think the approaches that are much more holistic and circular and looking at not only the recycling and reuse of materials, but looking sort of long term are, where we should be, because the problem is so big, as you say. Mm-hmm. Yes. I also think maybe the other thing I'll say is, and you're acutely aware of this, Jintu, in your work. There's so much exciting work happening in material science and fiber science that addresses sustainability in novel ways. Biomaterials, bioplastics, bio-based fibers that are responsive, that are living there. There's just so much fantastic work happening that are shifting away from a petrochemical paradigm. And I wish more of it was reaching industry. And so those roadblocks that take time, there are litigious issues, there are building codes, like they're in the States, the building codes are, from the 1960s. So there are those, how we get the science into industry, I think, is another big question. So the people who are making that happen, that's pretty exciting.
Yeah, thank you. Actually, you triggered me because I'm starting a new project to recycle textiles for materials useful for interior, at least interior decoration, and many other things. So maybe not now, maybe in a year time, I will produce enough materials, and then we can explore possibility of collaboration. Yeah,
I would love that. That would be wonderful.
Very interesting. But I think my colleagues may also have questions. Yeah. Okay. Any questions from the audience?
Hello, I have a question.
Okay.
Hi, Mohammed.
First of all, thank you for your beautiful presentation. I'm really fascinated by the interdisciplinary approach. But I have a question regarding some critics that argue that experimental architecture can prioritize innovation in theoretical concepts over practicality and functionality. So, how do you address concerns that experimental architecture may not be always suitable for everyday use or long-term sustainability?
Yeah, thank you for your excellent question. Yeah, I think the work that I produce in my practice, the projects operate with sort of between. I had the slide where I outlined our three sort of processes and phases, and they're situated between prototypes and also addressing issues of the built environment. And so many of the projects, including Ada, for example, they're prototypes. They're demonstrator projects that showcase what can happen, right? And where these integrated and situated technologies that work with AI could be integrated into, for example, a building facade. And that was something that we, with Microsoft, we're really excited about as a phase 2 project. So while they may be experimental in the eyes of people right now, we're always looking ahead as to what are our next steps. And just like you see with the pioneers of digital fabrication, which I am proud to count myself as one of those people, a lot of those people, Andrew Kudlis, Occam Menges, Roland Snooks, Neri Oxman, many others are no longer operating within the spaces of the gallery. I mean, the museums and galleries were our support, right? They were the venues that were allowing for the work to be supported and shown and to develop the experiments. But now increasingly you're seeing those same architects and engineers developing built projects in the environment that are functional and performative and really sort of pushing the boundaries. So, and maybe the last thing I'll say is there's a role for experimental architecture, right? There always has been. And it opens possibility. And for me, you know, I could not practice. I could just focus entirely on my lab and my research and my teaching, but I've always been deeply invested in how the work is materialized in a built environment. And so for me, it's an important step. It's an important part of the work and situating how research meets practice and how practice impacts research as a set of feedback loops. And in some projects, there are more practical, applications, and in others, they're much wilder and about sort of pushing the envelope. And I'm okay with that. That's what I do, and that's where I can make impact. And as I said in describing Lumen, and we're increasingly getting permanent commissions especially with the large scale canopy projects, which I'm super excited about. And, for me, the success of that project, as I mentioned, was seeing how people took ownership of it. And if my built work inspires a moment of pause and wonder in one's day, for them to maybe think like, wow, what's going on with this material? If it inspires a kid to think about science in a different way, I've done my work. Or to think about sustainability in a different way, that sustainability isn't just about metrics and performance and optimization, that it's also about beauty and phenomena and how we engage with our world. So yeah, that's my answer to your important question.
Thank you so much.
Any other questions? No more questions? Okay, if not, let's thank Professor Sabin for the most interesting, informative, inspiring talk. Yeah, thank you. Thank you, Jenny. Yeah. Thank you for your
Well,
time.
thank you.
Yeah.
Of course, yeah,
Let's
and thank
keep
you
in
for the
touch.
opportunity.
Yeah, yeah.
I look forward to staying in touch and to possible collaboration down the road.